In a sense, humans are creatures of light. I mean, in order to see this, many examples suffice. One, for example, is to go to the beach on a sunny day. You'll find it full of people. Lots of us are familiar with the properties of light. It has brightness and color. Scientists call the former intensity and call the latter either frequency or wavelength. And Maxwell's great discovery was that light is a kind of a wave. We have a few graphics to show us some of this. It's a kind of wave, but the thing that's interesting is that it combines two different oscillating objects, or objects in quotes there, or more formally fields. There is an electric field and a magnetic field associated with light. Remember, I told you it was a game of leapfrog, so you have to talk about both of them. On this animation, what I've done is try to show you these two objects, these two entities, these two quantities that we call fields. The blue balls, which you can see laid out along the x-axis, you can think of as electrical fields. The green balls, as you see laid out along the z-axis, which is up and down, you can think of as a magnetic field. And then as a wave of light goes by, the two of them actually oscillate together. And there you can see the electric field sort of vibrating in this plane and the magnetic field vibrating like that. So that's what light is. It's a dual vibration of electricity and magnetism. That was Maxwell's great discovery. Well, it turns out light has another property called polarization. And polarization is a little bit more difficult to get our minds around, as some people say. So we're going to do this in several steps. Again, in order to simplify things, I'll forget about the magnetic field and only talk about the electrical field. So here's another picture of a light ray. And if you look at this, you see it has a characteristic shape of a wave. You'll notice that there's a crest on the left-hand side of the image, as well as a crest on the right-hand side. If you go the distance between these two, that's what scientists call the wavelength. And interestingly enough, for light, that is exactly the definition of color. If you know the crest-to-crest distance of a light ray, you know its color. And for humans, we can only perceive light when it's in a particular range. So outside of that, the light is there, but we can't see it. But within this certain range, we can, and that's typically the colors of the spectrum in which we see. Now, this property called polarization, we're going to approach in two different ways. Let's imagine watching the electrical field as it comes towards us. One thing that it can do is simply vibrate up and down. And then that's what we scientists call linear polarization. Another thing that it can do is actually more interesting, which is what we call circular polarization. When a circularly polarized light ray approaches us, if we watch the electrical field lines, they rotate around. In fact, I have an animation to show both of these, and here they are. In the middle, we're going to watch linear polarization. What we'll find is that the blue line will simply go up and down, and that's what linear polarized light is. The electrical field vibrates only along a single line. The two green arrows that you see in this illustration, however, will wind around as we watch them, and that's what we mean by circular polarization. The electrical field line, in that case, winds around. So here we set the movie into play, and there you can see the linear polarization with the blue line going up and down, but each of the green lines moves around in a circular path. Now, this last property of polarization is there in the mathematical description of light, but most of us cannot detect polarization with our eyes. But interestingly enough, it turns out some people can actually see polarization. This was first discovered by a geologist by the name of von Heidinger. And in 1846, he noticed that he could actually correlate a particular image with the polarization of light. This effect is now called Heidinger's brush. And it's due to some peculiar natures of the structure of the human eye. In fact, cameras cannot see polarization, but people can, and it's even a skill that you can learn. So it turns out that the way that Heidinger's brush works for those who can see it, and let me tell you, I'm not one of them, but I've read the phenomena, is that when someone who's sensitive to polarization actually looks at a bright sky, they will see a diffuse pattern that, roughly speaking, looks like two figure eights. One of them is vertically oriented, the other of them is horizontally oriented. And that figure eight shape is actually caused by the polarization of the light. So when such a person looks at a bright sky, if they turn their head to one side, it will seem as though that figure eight will rotate one way, and that will be caused, for example, when the light is polarized, such as we see in the circle that I'm pointing to in the image. Let me set it in motion to remind you what happened. So there we see one of the polarized beams. So for a person sensitive to polarization, when they turn their head to the side, they actually see this figure eight rotate one way. If the light is polarized in the other sense and they turn their head to the same side, the figure eight tilts to the opposite direction. That would correspond to the circular polarization that I'm indicating with my pointer here. And if the light is linearly polarized, then the figure eight doesn't move at all. It just, they turn their head and it still keeps the same orientation. And that corresponds to the center image where we see the light, the electrical field associated with the light beam simply vibrating up and down. This is quite remarkable. In fact, before I was preparing this course, I was not aware of this phenomenon, that there are actually people who are sensitive to the polarization of light. And I think most of us are totally unaware of this optical phenomena, but apparently some people are. So that's what polarization of light is. It's actually detectable by a small number of us. We have many, many devices for detecting polarization. And in fact, polarization actually is something that we could take advantage of in constructing things like polarized glasses. Let me show you how that works. Here we have, again, a depiction of our electrical fields. It's the balls that you see lined up along the axis that the pointer is indicating. And now, if we set an electrical field in motion, you'll notice a wave starts to form. But we have an object that's blocking the wave, and when that happens, the wave never makes it through the object that's doing the blocking. In terms of light, that means that if we think of this light coming in, if we have this orientation that blocks it, then the light that goes through doesn't make it. On the other hand, we can also say, well, let's rotate the object doing the blocking. So here we see this, and again, we set up a light ray. It comes through, but because the orientation of the blocking object is exactly lined up with the electrical field or the light makes it to the other side. Now, although these are simple models, we actually know how to build these things. They're called Polaroid glasses. The reason Polaroid glasses cut down on the amount of glare that one sees in a day is because glare typically comes off of a surface with what's called a horizontal polarization. So if you have, that means that the electrical field line is moving like this. So if you set up your opening and your blocking so that it does like this, it means that light doesn't get through and you don't see the glare. So this is how Polaroid glasses actually work. Now, of course, all of this is real physics, and several times during this presentation, I'm sure you find yourself asking, why in the world is this guy telling this stuff that has nothing to do with string theory? Well, the reason is because every single physical phenomenon that I have described, in fact, has an echo, has a remnant that shows up in string theory. And today's lecture is going to be about how the analog of Heidegger's brush was used in 1984 to construct a new string. You will remember at the end of our last lecture, we got to talk about anomalies. Anomalies were phenomena that occur because the world of the quantum is complicated and motion can occur in ways that we could never see in the world around us. For currents or charges that move in the quantum world, if you put some charge into a wire, you would like to get the same charge out. That's called current conservation or charge conservation. But in the quantum world, because the objects are free to wander, not all the charges you put in come out. And when that happens, we get an anomaly. An anomaly, as we discussed in the last lecture, was a horrible thing to have around. So Green and Schwartz looked at the mathematical properties that were associated with anomalies in the string, the superstring, first constructed explicitly in 1982, and they found an amazing result that if you have exactly 496 charges, then the string would have no anomalies. It would be as if you put 496 different colors of balls in our example, and every time you put one of the balls in, for every ball you put in, one would come out. That's the current conservation. That's the great discovery of the superstring. Now, this 1984 construction, which completed the anomaly freedom of the string theory, actually led to a puzzle. In my last discussion, I explained to you in some sense where the number 496 appears in mathematics. It's the number of rotations that one can perform in a mathematical world in which there are 32 different directions about which one can perform rotations. Now, if one looks at that, at an earlier stage, we were talking about rotations. In some lectures ago, I talked about the fact that there's a particular form of mathematics that's exactly associated with the idea of rotations, or more generally, what physicists and mathematicians like to call groups. So when you have something like 496 that works for a particular set of rotations, you can go often to the mathematical literature to study the properties of these things. And roughly speaking, this occurred after Green-Schwarz anomaly freedom was discovered. In fact, they realized almost as soon as they wrote the paper that in addition, in fact, the comment is actually in the same paper, that in addition to the rotations around these 32 axes, which gives you this number 496, there's another way to get the number. Now, this other way was actually discovered by a mathematician. In fact, it's the mathematician Quartet, who we've mentioned several times previously in these discussions, who was really the person who pulled together the idea of how to describe mathematical objects that are the most general possible that are similar to rotations. Now, when Quartet actually solved the problem of finding the most general mathematical rotation, he observed that there are lots of different possibilities, but there's one possibility that's extremely exceptional. In some sense, it's the most complicated rotation that one can describe using these mathematical formulations. This particular set of rotations goes by a name. It's called E8. The E stands for the word exceptional. And now the interesting thing about E8 is if one thing about rotations to keep in mind is that rotations are described by angles. When you rotate something, you can always talk about by how much angle I rotated. So if you have 496 rotations, there must be 496 angles that tell you by how much the rotation was performed. Well, back to the story of E8. Turns out that the mathematical object E8 has exactly 248 rotations and therefore angles associated with it. Well, you don't have to be Einstein to figure out that 248 plus 248 is 496. But 496 was the magical number that prevented the anomalies from causing havoc in string theory, in superstring theory. So it was therefore a puzzle in 1984 that if we found this one set of mathematical rotations for which the superstring was a consistent theory, then why not the other set? And this led to a very great puzzle. Now, let me say a little bit about the SO32 string, because it has played an important role in understanding string theory. We described how the string itself is kind of like a filament, but one thing about the SO32 string is that if you ask about these charges that I described earlier, these 496 charges, one physical question you can pose is, well, where exactly on the strings do these charges occur? And the answer turns out to be rather interesting, because for the SO32 string, what one has to do is to consider both open and closed varieties, and you can put the charges at the end of the open type of string. Now, before 1984 or 1985, this was the only way in which physicists knew how to describe a string that had charge. Namely, it carried charge at the end of the filament. The middle of the filament never carried charge. So there's something interesting going on here. because now we get into the business of whether the string is a little hoop or whether it's a filament, because the charges are always at the end of filaments. Now, that's kind of strange, because why must the charges only be restricted to the ends of filaments? And in fact, one of the really interesting parts of this question is that a moment ago we talked about light, how you could have linear polarization where the electrical field simply goes up and down, or you could have circular polarization where the electrical field seems to rotate in either a clockwise or an anti-clockwise sense. This is actually related to string theory. Some lectures ago, I talked about the fact that a closed string actually must have the properties that are very similar to having a sound wave in a pipe. Perhaps you remember that animation. If you have a closed pipe and you look at the average displacement of the air molecules at the ends of the pipe, they're not allowed to move. So you see a bow shape that is tied down at the ends. If you have an open pipe, the ends are free to oscillate back and forth. In string theory, this exact same mathematics occurs. The closed pipe corresponds to a string whose ends are tied together. These are the kinds of strings that always describe gravity among the particles that seem to occur as specific oscillations. The open strings, the ones that have the charges at the end of them, always describe things like photons, but they never describe gravity. So we have a picture here then that if you want to describe a theory with both gravity and with charges, it seems like you have to have a string that combines both open and closed. And since the open strings have the charge at the end, that's the only place that you find the charges. Well, in 1984, a remarkable occurrence happened in Princeton University. This discovery was led by David Gross, a recent Nobel laureate in physics, but for a different work, not this work which we will describe now. It is as if David Gross, Emil Martinek, Ryan Rohm, and Jeff Harvey were mathematically able to perceive Heidegger's brush. Remember, I talked about polarization. Not many of us can actually see it, but there are some people who can. Well, in some sense, what happened in 1984 is that this group at Princeton, these four physicists at Princeton, became mathematically conscious of the fact that there was a kind of brush associated with open and closed strings, particularly with closed strings. And they used this to their advantage. By the way, this group of physicists, since there are four of them and they were at Princeton, we now refer to them often as the Princeton String Quartet. So what did the Princeton String Quartet actually do? Well, in order to understand their work, we need to go to look at closed, open strings. So here's a picture of a string. This particular picture I have is of a closed string, and in a moment we'll set it into motion so that we can actually watch it moving. And we imagine that we've deformed it, and now let's set it into motion. There it goes. As you can see, it's oscillating back and forth, but one of the interesting things about these oscillations is that, as you can see where my cursor is right there, the string is actually not moving at that point. That point of no motion is what we physicists call a node of vibration, a point that's fixed even though the extended object is moving. And as you can see in this picture, the node, there's not just one node, so here's one at the cursor here. There are other nodes, so let me go to another such node. You notice I can put my cursor there and I'm always touching the string even though it's vibrating. So this particular string, this closed string, the one that is mathematically described by this picture, has nodes in it. And now there's something very interesting about those nodes. They all sit at the same place as we watch the string vibrate. What David Gross and his collaborators realized was when you looked at the mathematics of closed strings that had been written up to 1984, every mathematical description of a string had this property that the nodes of the closed strings always sat at the same location. Well, once you have the idea that these nodes sit at the same location, roughly speaking, that is like looking at light. So here's our light once again, like looking at polarized light, and realizing that this is the analog of the middle picture here, where the electrical field simply goes up and down, but it never actually rotates. It only touches the sphere at two places, either at the top or when it rotates all the way down to the bottom, touches at the bottom, but those are the only two places. So in the first figure, if you ask, where does the light touch the circle? It's at two places. One's at the top, one's at the bottom. That's like the nodes that we saw in string theory. So once you know these nodes are here and understand the connection to polarized light, the next most natural thing to do is ask, in the mathematics of string theory, is it possible to introduce objects that correspond to polarized light? In other words, whether we can find mathematical objects where when we watch the electrical field lines, what we see is that they rotate around as the upper two examples do, as opposed to just touching the circle at a single point. Now this is actually important for string theory, because you see, if we can find such a construct, then the charges on the string do not have to be just at their ends. The charges can be distributed throughout the length of the string. So David Gross and his collaborators set out to find such a construct. And of course, since we're doing the mathematics by pictures as opposed to actually writing the equations, it's pretty easy for us to figure out what we need. Here's such an example. Here again is a string, very similar to our first, and now let's set this one into motion. And you'll notice the nodes move in this one. That's different from the closed string. The nodes move, and in fact, we call such motion left movers or left-handed motion. So that, roughly speaking, corresponds to a kind of left circularly polarized light. In a similar manner, if you can write this mathematics, then gee, maybe you should be able to write the mathematics which describes right movers. And so in this famous paper of 1984, indeed, the Princeton String Quartet were able to describe right movers, where the nodes move in the opposite sense. And so a new kind of string was born. Now you'll remember I talked about the mysterious number 496 and how in the original construct of Green and Schwartz, they saw that SO32, that is rotations in 32 dimensions, would lead to this number. Well, what Gross and company did was to write down the mathematics that took advantage of Cartan's second observation about how to get the number 496. You can get it from two E8s. 248 plus 248 equals 496. And this construction has a very interesting interpretation, because you can also interpret this kind of construction, which is called the heterotic string, as being the logical bringing together of strings that live in different dimensions. That is, you imagine that the left moving string is a superstring, and we've talked about what that means. It has spin associated with it. But all the right moving parts of the string are associated with the old bosonic string that had the tachyon problem. Remarkably enough, this synthesis works. And when you study the synthesis, you find out that the problem with tachyon is banned because the supersymmetric part of the string, which is sort of the left part, actually gets rid of tachyon. On the other hand, the right-hand part of the string is like an open string, and that allows the charge to be distributed throughout the entire heterotic string. So heterotic string theory was this amazing synthesis that truly set off a revolution after it was born in the period 1940 to 1985. And if you look at the physics literature, you'll find an enormous number of citations in the literature about this. Now, this bringing together, geez, that sounds like a bit strange sort of thing. It certainly was very startling, because when it was done, no one first thought it could be done. In fact, I remember being on a visit to Berkeley, talking with a friend of mine who's a mathematical physicist, who said, well, gee, how can you actually do this business of making the SO32 and the E8 cross E8 work? Fortunately, this bringing together mathematically had the parts necessary lying in the physics literature. Two physicists, one by the name of Sakamoto and another by the name of Siegel, had provided precisely the mathematics that tells you how to bring these parts together. One of these, the one by description by Siegel, uses a piece of math we call chiral bosons. That basically means a mathematical object that describes something that spins around. And when you put these things together, then you find that you can describe the heterotic string. Well, not quite. There's actually a little bit of a puzzle here. Remember I kept talking about 496 and how that was the magic number of charges? Well, in fact, if you do the description, if you look at the description that Gross and Company wrote in 1984, you'll find out that they don't actually introduce 496 of anything. And so then you have to wonder, well, where are the charges that we're talking about? This part of the story has a very interesting connection to a gentleman, a Scotsman, in fact, who was out riding his horse in 1834. His name was John Russell. And one day while riding at the Union Canal near Edinburgh, he observed a single wave that formed. In fact, let me read his description of this. He said, "I was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses, when the boat suddenly stopped. But not so the mass of water in the channel which had been put in motion by the boat. It accumulated around the prow of the boat and then rolled along with a great velocity, assuming the form of a large solitary elevation, a rounded, smooth, and well-defined heap of water which continued on its course along the channel without change of form or diminution of speed. He followed it on horseback and did so for several miles." This strange wave that he observed in the canal is something that we've actually seen a number of times in physics. In fact, I have an animation here. Normally we think of waves as the nice gentle sort that you see rolling in at the beach, and they come in one after the other. You don't see solitary waves. The kind of wave that John Scott Russell reported that day was sort of something like this, where you see a single solitary wave as it moves along a channel. Now, this kind of wave is very special. Even though it's a wave, it actually has properties of particles. You know, particles, after all, if you take two particles and bump them into each other, they bounce off of each other. Ordinary waterways, if you collide them, actually pass right through each other, but not these objects. If you take these waves, these solitary waves, which we call solitons, then in fact, they have the properties of particles. A very strange result. Solitons, in fact, have been observed even to this day we observe solitons. For example, there are pictures that NASA takes of the ocean where you can actually find single large solitary structures that stretch out for hundreds of miles, and in fact, they're examples of these solitons. So solitons are a feature of our world. They're waves, but they have the properties of particles. And now, remember this mystery of the 496? I told you that Gross and Company didn't have 496 anything in their work. Well, the point is that the bosons, or an alternative description called chiral fermions, also called heterotic fermions, can be used to describe solitons. And in fact, if you look at the original paper of Gross and Company, what they do is say that the charges that make this magical number of 496 are distributed between the ordinary waves of their theories, the things that are described by the chiral bosons or the chiral fermions. These are mathematical words for ordinary waves. And then they need to find the remainder of this 496. It turns out that when you study these ordinary waves, the equations for the ordinary waves in the theory, you find out that if you add up all the ordinary waves and all of the solitons that these waves can describe, these single waves that we've seen in our animation, the number adds up precisely to 496. So in a sense, the heterotic string, which is the thing perhaps that most forcefully tells us that Einstein's dream has been realized, because the heterotic string is different from the SO32 and makes it glaringly obvious that unification of the type that Einstein wanted, his so-called unified field theory, is a mathematical reality. In a sense, this successful construction of the heterotic string owes part of its intellectual debt to a Scotsman who was out riding his horse in 1834 and observed a solitary wave and tried to write equations to describe it. The same phenomena was what was necessary for the success of the heterotic string in Princeton